notification of recording, you need to click OK. Yeah. Yeah. What was that?
Oh, no, that means that I'm sharing my screen. Ah, I say OK.
Yeah, yeah. Test. Yeah. Okay, it's my pleasure to welcome today's speaker, Barbara Benedikt. Barbara is a fourth-year PhD student at the TU Darmstadt under the supervision of Professor Mark Fischlin. Her primary research interests include quantum algorithms, quantum-annoyance, and quantum security notions. Her work in this area has resulted in publication at AsiaCrypt 2023, AsiaCrypt 2025, as well as a single author contribution to post-quantum cryptography to PQCrypto 2025, which was awarded Best Young Researcher Paper. Building on her formal background as a mathematician, she has recently broadened her research focus to encompass efficiency aspects of classical cryptographic protocols. Today, she's going to share with us her AsiaCrypt publication on the order of hashing in Fiat-Shamir schemes. Without further ado, the stage is yours. You can just click this on your color.
Hi, everyone. Thank you for the kind introduction, Xiao, and thank you all for coming and joining my talk. My name is Barbara, and I'm happy to be here today and present you my most recent paper. It's a joint work together with my supervisor, Mark Fischlin. But before we dive deep together into the technical part of my talk, I would like to take a few minutes to introduce a bit more myself and also my university. So as Xiao said, I'm from TU Darmstadt. This university is located in the city Darmstadt, which is pretty much in the middle of Germany. And maybe you find that funny that I said that it's a city, because I guess it's located there at the low red point. And I guess for Hong Kong standards, it's not really a city with its 170,000 citizens. But it's pretty much a university city, as it has 40,000 students. I also want to share some pictures with you of my university. On the top row of that slide, you can see a picture of the new main building and also of the old main building of my university. And in the lower row, you can see the so-called cybersecurity building. This is where I work, and my office is roughly located there. However, Darmstadt is just the city where I work, but I don't live there. I live in Frankfurt, which is a red point in the north of Darmstadt. And maybe you know Frankfurt because it's one of the more famous cities in Germany. And I guess reasons for this are maybe that picture, because Frankfurt is actually the only city in Germany which has a skyline. And I guess for Hong Kong standards, it's a pretty small skyline, but Frankfurt is very proud of it. And sometimes we call that district also Manhattan. It's like a small joke because of Manhattan in New York. And that river here is called Main, so it's Manhattan. I don't know. And here in the top right corner, you can see the European Central Bank. This is also in Frankfurt. And yeah, as I said, when I'm in office, I'm commuting. And to bring my commute maybe back to Hong Kong standards, I realized that the distance is pretty much the same as I would live in Hong Kong Disneyland and would commute like every day or to the university. However, I'm afraid that my preferred way of commuting, which is taking my bicycle, wouldn't really work on that route. Yeah, with that, I actually also wanted to reveal one of my hobbies, which is cycling. And if you pay,
How do you commute during raining day?
I have clothes. Like,
Okay. But you still ride bicycle?
Yes, I try to. So snow is the exception, then I don't like to go. with a bicycle, but yeah, Germans say there's never bad weather, just bad clothes. I don't know. Yeah, I also want to share some more of my hobbies with you. If you pay attention to the next slide, you can maybe find some more hints. But yeah, before we continue, I'd like to briefly check your background so I know how much to go into the details on the next slide. So please raise your hand if you're familiar with cryptography, just with crypto. Almost everyone.
Turn the air conditioner
Okay.
on. Not sure.
So almost experts in the audience. Are you familiar with hash functions? With signature schemes? Random oracle model? Okay, okay. So it's mixed, but almost only experts in the audience. Okay, so then let's come back to the topic of today's talk, the order of hashing in Fiat-Shamir schemes. And here's a roadmap I have planned for today. So I will start with an introduction to Fiat-Shamir schemes and explain the motivation of our paper. So why we actually should care for the order of hashing and why it deserves a closer attention. One reason for this is for sure that Fiat-Shamir schemes are very important in real-world applications and widely used in practice. And yet we find different standards. We find from standards to standard different hashing orders. And we will take a closer look to that. Then I will summarize the main contributions of our paper. And afterward, I discuss them in more detail. So in particular, we defined a new multi-instance security notion for signature schemes, which we call annoyance. And then we also analyzed all hashing orders with respect to this new security notion. And then I will conclude with some open questions and ideas for future work. At this point, I want to make a final note before we jump into the introduction. If there's something unclear, if you have any question, then just feel free to interrupt me. Okay, so let's begin. What is a Fiat-Shamir scheme and why should we care about the order of hashing? In 1986, Fiat and Shamir proposed a paradigm how one can transform an identification scheme into a signature scheme. So let's begin with the identification scheme. In such a scheme, we have a prover, who is Alice in that picture. She has a secret key and a public key. And on the other side, we have a verifier to whom Alice wants to prove her identity. That means that Alice wants to convince the verifier that she actually knows the corresponding secret key to the public key pKa. How does she do that? She starts to send a commitment to the verifier. By the way, so the identification scheme is a non-interactive, and the signature scheme later is, of course, a non-interactive scheme. Okay, so Alice starts to send a commitment to the verifier. And the verifier then computes a challenge, CH, based on Alice's public key and the received commitment. Given this challenge and her own secret key, Alice provides a response for the verifier, which finally convinces the verifier to trust in her identity and to believe her that she actually knows the secret key SKA. How does the Fiat-Shamir transformation change this picture? It turns this interactive identification scheme into a non-interactive signature scheme. But first, what exactly is a signature scheme? A signature scheme consists of 3 algorithms, which allows a user to produce a digital signature for a digital document. So we have a key generation algorithm, which outputs a secret key and a public key. We have a sign algorithm, which allows a user to sign a message. And we have a verify algorithm, which checks whether a given signature on a message is valid or not under a public key. And if it is valid, it outputs 1, otherwise it outputs 0. And the key idea is why we use here the secret key and here the public key is that only the holder of the secret key should be able to generate a signature, but everyone else should be able to verify that the signature is actually valid. Okay, let us come back to that picture. The Fiat-Shamir transformation changes the identification scheme into a non-interactive signature scheme. So here you remember that arrow was the other way around in the picture and the interaction disappeared. So the challenge is no longer computed by the verifier, but by Alice herself. She computes the challenge based on the public key and the commitment. This is as previous, but also based on the message she wants to sign. And then the final signature consists of commitment, challenge, and response. And this can be verified by everyone together with a message. How does Alice compute this challenge? In an ideal world, she feeds all 3 components, message, commitment, and public key, into a monolithic random oracle. And she uses the output as the challenge. So what is a random oracle? You can think of a random oracle as a perfectly random function. It takes any input and returns a random output. But the important thing is that the random oracle is doing this in a consistent way. So what it does is for any input query, it checks whether it was queried before. If so, it returns the output it responded before, and otherwise it samples a fresh random value. And what I mean by monolithic is that it takes the input as a single block, so it doesn't divide it in any smaller blocks and process them one by one. Why do we like the random oracle? So cryptographers usually likes it because it idealizes hash functions, but also pseudo-random functions and other related primitives. And this model makes it easier to write security proofs. And there are also some results that are only proven in the random oracle model and not in the standard model in the real world. And the downside of this model is that it's just an idealization, as I said. It's not the real world. And actually, there exists a construction, which you can find in that paper, which is proven secure in the random oracle model, but it is insecure with any concrete instantiation. Okay. So that was just a short explanation. Let us come back to that picture. So in which order should Alice, when she is computing the challenge, in which order should she input message, commitment, and public key into the random oracle? Well, that's hard to say. In practice, we are actually dealing with a whole zoo of Fiat-Shamir signatures. Just for Schnorr signatures, which are a well-known signature scheme in cryptography, it's based on the discrete logarithm problem, and it's really widely used in practice. For these schemes, we already can find 3 variants. In Schnorr's original paper, and also the ISO standard, suggests to hash the commitment and the message in that order and without the public key. Whereas the Internet Research Task Force,, suggests to put the public key in the middle And Bernstein, in one of his papers, recommends to put the public key in the beginning. And if we go a step further and look at the post-quantum signature scheme MLDSA or CRYSTALS-Dilithium, we encounter yet another variant. On one hand, the order is completely different compared to the others. And on the other hand, the scheme applies the hash function 3 times instead of once. And seeing this diversity, there comes actually a question to my mind. Does this mean the order doesn't really matter? So can we just do what we want? And the answer might be yes in the ideal world, where the hashing is done by a monolithic random oracle. All 3 components are fed as one single block. But in the real world, we don't have monolithic random oracles. The hashing in the middle is usually done by a hash function like SHA-2 or SHA-3. These are so-called iterated hash function. This means it takes the input and divides it in message blocks and processes them one by one. So it's really non-monolithic at all, and also not a random oracle. Keeping the zoo of Fiat-Shamir signatures in mind, we arrive at a natural question. So in which order should we hash? Does this matter? And this brings me to the contributions of our paper. So our first contribution is that we defined a new multi-instance security for signature schemes, which we call annoyance. And this notion differs from standard security notions as it considers multi-instances of signatures. To make that point clear, it makes sense to go to the standard definition or the standard security notion for signature schemes, where usually only single instances of signatures are considered. And this standard notion, which I mean is the existential unforgeability, what that means is even if an adversary can ask for many signatures of messages of her choice, she still cannot produce a new one. More concretely, how the security game looks like. So we have an adversary and we have a signing oracle. And the adversary can choose multiple messages and ask the signing oracle for signatures to that. And our adversary wins that game if in the end she can output a fresh, so it means that this forgery, so a valid message signature pair, was not provided by the signing oracle. And I would call this a single instance security notion because the adversary already wins the game if she can provide one single forgery. And in contrast to that, in our multi-instance security notion of annoyance, our adversary must provide many signatures and also possibly to signatures which correspond to multiple users. And since in the real world, if we have a signature scheme that is deployed, many users can use it, this multi-instance security captures the reality more realistically, the practice more realistically. So, the second contribution of our paper is that we analyzed all hashing orders with regards to that new security notion. And in doing so, we came up with a simple rule which answers our original question. When using Fiat-Shamir signatures, one should hash the commitment before the message. However, not every Fiat-Shamir scheme is within the scope of our paper. We only consider hash functions, which are either based on the Merkle-Damgård construction or the sponge design, like SHA-2 or SHA-3. Let me briefly recall these paradigms. Let me begin with the Merkle-Damgård construction, therefore. So there we take the message, we divide it in blocks of bit length b, We add here a padding. And then we process the message blocks one by one through the green box, which is called compression function. And we start with the initialization vector, which is of bit length n. And in that way, we kind of transform the initial hash state through intermediate hash states into the final hash value here. Yeah, and all the hash states have bit length n. In the following, we will stick to that picture of how we compute hash values, but we simplify that picture a bit. We will represent it as a graph, and each node in that graph represents corresponds to a hash state, and each edge in the graph corresponds to a message block. So instead of that picture, we will consider that picture, which is a bit more handy to use, I would say. This was the Merkle-Damgård construction. How does the sponge construction look? In a sponge construction, we do not have a compression function as before. We have a permutation f, which is also called the sponge function. The message blocks one by one through this XOR, and then we feed everything into the permutation.
So this is within the construction SHA-3, or it uses SHA-3 as a part of F?
SHA-3 is
you said, for example, this is a construction SHA-3.
Yes.
Oh, so in SHA-3, do you know how do they implement the F?
It's called Ketchuk function.
Oh, I see.
And it's some wild permutation. Maybe you can look into the standardization.
I see.
I didn't.
It's not something as easy as, for example, I can just use AES as a part of F, right? Because AES is a permutation, but they are actually using something much simpler.
Yeah.
Okay.
So it's called Ketchuk function. I'm actually not sure if they use also part of AES.
I see. It's okay.
So the first phase where the message goes into the computation is called absorbing phase. So remember, we call this thing a sponge. So we absorb the message.
Oh.
And then in the second phase, we squeeze out the hash value. So this depends a bit on which size of hash value you want to have. So it could be that you have more squeezing steps here, or just one squeezing step. So it really depends on what you want here as your final value. And if we look to SHA-3, for example, we only have one squeezing step. Okay. So this doesn't happen anymore. At first glance, this construction may look completely different as before, but actually the Merkle-Damgård construction fits into that picture. If you imagine this XOR with the permutation as a compression function, and just allow one squeezing step, which is in SHA-3 anyway the case. So for the sake of simplicity, I won't distinguish between those two design paradigms anymore in my talk. And we further assume that this green box is behaves like a random function. So that was the first restriction of our paper. The other restriction is motivated from the examples I showed you before of Schnorr signatures and MLDSA. We only consider challenges which are of what we call plain or nested form. So plain form is where we apply the hash function only once, and the nested form is where the hash function is applied in a nested form. And for convenience, I will only focus on these kind of challenges in my talk. Okay, so when is such a scheme annoying? Following the intuition of Eaton and Stebila, who were the first one who defined quantum-annoyance for password authenticated key exchange, or PAY, we call a signature scheme annoying if an adversary must start from scratch each time she attempts a forgery. So more precisely, suppose we have one forgery text, so an adversary who only outputs one forgery with runtime t, such that any L forgery adversary, so adversary outputting L forgeries, has a runtime of at least L times t. In particular, this means that any computation such an L forgery adversary has done for one forgery attempt that cannot be reused for any other attempts. Otherwise, he could reduce his runtime. However, in practice, this is usually not possible to achieve because we have this compression function which is fixed, and an adversary can generate a very large table with pre-computed values of the hash of the compression function, and get on that way some advantage. So that's the reason why we relax the definition to so-called epsilon annoyance. Epsilon annoying means that outputting one forgery or L forgeries scales with a factor of epsilon.
Is epsilon a function of L, or is independent of L?
It is dependent of L.
So how should I think about it? It should be proportional to L, or?
So ideally, it is just L, or very, very close to L, because then the scheme is not
again,
annoying.
why don't you say 1 minus epsilon times L, or epsilon times L, if you want a relaxation on L?
Yes.
Should I think it as some constant times L?
No, it could be some function. So I will later show you example where it's logarithm of L or square root of L.
Also, do you put any restriction on T?
No. No, so we are looking at unbounded adversaries.
Because you are in a random Merkle model, so you don't put a restriction on the computational time, but you just bound the number of queries?
We are just interested in how, yeah.
You just count query complexity?
Yes.
Oh.
Yes.
Yeah, otherwise, if you set T to be exponential, then no scheme is annoying. Because, totally break it.
Yeah. Maybe that makes more sense. So, formally, we say a scheme is epsilon annoying if there exists a one forged adversary. You can think of him as like the gold standard, the best adversary who is outputting one forgery, such that for any other adversary outputting L forgeries, that epsilon times the runtime of A1 is the lower bound of our adversary AL.
Let me clarify this.
Yes.
This definition should apply, say, for example, Schnorr signature. Right? Would you say Schnorr signature is epsilon annoying for some epsilon?
I mean, in the worst case, epsilon is 1. Like everything is 1 annoying. It's just
I see.
interesting.
Good. I see.
What is epsilon?
Okay.
Yeah.
My concern is actually if you consider Schnorr's signature, if I have exponential time to break DDH, then you cannot configure any other epsilon other than 1. right? If my t is exponential, ta1 is exponential, then only epsilon equals 1 makes sense.
Yeah. I think the difference is that like we're not like trying to attack the scheme directly. We're just focus on the random oracle model, but now not as if you have the picture of Merkle-Damgård constructed, we are not applying the random oracle model to the whole thing, but to the conversion function. Yeah,
then maybe if you are saying that, maybe you should define this notion for the hash function, like as a security parameter property for the hash function instead of the signature scheme. Because if the signature scheme could be the combination of the hash function and other computational hardness assumptions, right?
So we do it like on a more abstract level for Fiat-Shamir schemes where we have some.
Oh, I think this could be a potential research idea. Like, for example, I can define collision resistance with this. Your time you found one collision.
Yeah.
Compared with the time you found a L collision.
Yeah.
I can define this and study that property, right? Good. Yeah. I see.
Okay, so let us continue with the attack model for an L forgery adversary. It's a bit different than the model or the game I showed you for the existential forgeability. So of course we have our adversary. And this time it's not just interacting with one signing oracle, it's interacting with a user pool with a lot of users. And this time she's not allowed to send multiple messages, just only one. And in return, she gets one signature, one valid signature for this message, but one signature for each of the users. And she wins the game if in the end she can output L forgeries, which were not part of that interaction, of course. And then one forgery attack is just a special case of it. So in that case, the adversary is not outputting L forgeries, but only one. And we further distinguish between annoyance for user exposures and annoyance for signature forgeries, depending on the outputted forgeries in the end. So an user exposure attack affects L different users. In that case, the outputted L forgeries in the end could potentially belong to the same message, whereas the signature forgery attack only affects one user, and here all the messages must be different. Depending on the capabilities of the adversary, we either say something is classical annoying or quantum. Okay, so let's start with the analysis. And find an answer to that question, how we should compute the challenge and how we should order all the components. If we take a look at the results of our paper, one can say for sure that putting the message at the beginning is a bad idea, because in that case we have epsilon equals 1 and no annoyance at all in the user exposure setting. Why is this the case? Remember that the signature consists of commitment, challenge, and response, and only for the computation of the challenge, the message became relevant. So in case we can find two messages which produce the same challenge, we can reuse the signature. So every signature which is valid for one of the messages is also valid for the other. How can we find such two messages? can do this by searching for a collision of the underlying compression function. This can be done, for example, by a birthday attack, so a brute force search, or if there is a quantum computer available, we can use Grover's search to do that. And let us take a closer look to Grover's search and how it can be used in this context. So Grover's search solves the problem of an unstructured search problem. So given a function f, which maps n bit strings to 0 or 1, with the guarantee that there is at least one input which maps to 1, Grover's algorithm outputs such an input after 2 to the n/2 evaluations of f. Whereas in the classical setting, one may evaluate the function f over the entire search space. So we get a quantum advantage of a square root here. How does the search algorithm work? The algorithm is based on amplitude amplification. So we start from a uniform superposition. And then with each iteration of the Grover search, we amplify the amplitudes of the desired elements, and we decrease the amplitude of all the other elements. So it could look like this. And after enough iterations, we get into a state which we can measure and then get a desired element with good probability, with high probability. And there's also another variant. If you imagine here, or if you imagine that there is not just one solution or one element which maps to 1, but more than one element, then this amplifying the amplitude of the desired element goes actually faster. So then in that case, if t is a number of such elements which maps to 1, the runtime reduces from square root of 2 to the n to square root of 2 to the n/t. How can we use it in the context of collision search? There is an algorithm by Rassat, Hoyer, and Tapp. I guess these are French guys, who showed that for a random function which maps n bit strings to n bit strings, there is an algorithm which outputs a collision xy after 2 to the n/3 evaluations of f. Remember, classically, it would be 2 to the n/2 due to the birthday bound. So we get again here a quantum advantage. How does the algorithm work? So we want to find in the end x and y which collide under the function f. And it starts by taking 2 to the n/3 candidates for the first component of the collision. It evaluates the function f and stores all the images. And then, just because the function is assumed to behave random, there are 2 to the m-2n/3 candidates for the second component. Why is this the case? If I fix an element, an m-bit string element, and an n-bit string element, then the probability that the one element to the other maps to the other is 1/2 to the n, because random function. So now we don't have just one candidate here, or one allowed image. We have 2 to the n/3 of them. So it's the probability that a fixed m-bit string maps to one of these values is 2 to the n over 3 over 2 to the n. So it's exactly that value here, the 2 to the minus 2n over 3. And as we, as we have here in our search space 2 to the n of these values, we get this many candidates for y. And in the second step, we just need to define the search function properly for the Grover search. And this allows us to find a collision after 2 to the m over 2. So this is square root of the search space size divided by square root of number of solutions, so number of the good elements, which is what we calculated here. So in the end, we expect to have to evaluate function f 2 to the n over 3 times. Okay, so let us return back to that picture. Once we found this collision, either classically or quantumly, we found two messages which map to the same hash value, so they also produce the same challenge. Remember, we are in the setting where the message is hashed first. And actually having this, I would call it like the black message and red message, found it is easy to run a user exposure attack. The adversary asks users to sign the black message, and then she can output the red message together with all the signatures she has received in the first step.
So the signature is the same, but the documents are different.
Yes.
But they verify that the forgery is a successful forgery.
Yes.
This is called exposure. I think I have a misunderstanding of user exposure. User exposures mean you just reuse the signature but make another message to consistent with the signature.
So user exposure means that all of the forgeries corresponds to different users.
Corresponds to different users.
So at that point, we ask all these users to sign the black message. So actually, we have here a lot of black messages with different signatures. And then we just reuse the signatures, but change the underlying document. And it still verifies because the messages were chosen such that the challenge stays the same.
Okay.
So the picture looks like this. Running a one forgery attack and running an L forgery attack has the same runtime because we only need to find one collision of the compression function. And we calculated before. So T is the runtime to find one collision. And it's pretty obvious in that case, epsilon equals 1, and a scheme where we hash the message first cannot provide annoyance for user exposures at all. Such a scheme is at most log 2 of L annoying for signature forgeries. So why is this the case? Oh, and by the way, here we have this function which depends on L, but not in a linear way. Why is this the case? This follows from Jou's multi-collision attack. The adversary searches for several succinct collisions of the compression function. And as a result, she knows many messages which all map to the same hash value. It's L messages, L different messages, and all these messages produce the same challenge. And again, having all these messages, it's easy to run an attack. This time, the adversary asks just one user to sign one of the messages, maybe just the straight one, and then she can use all the other messages she has generated together with this single signature she received. Yeah, and that way she can run a successful forgery attack, which has the runtime of log 2 of L finding log 2 of L collisions. So in that case, the epsilon factor is log 2 of L. But as we're not, it's not known that this attack is actually optimal. We only can say that it is at most log 2 of L, because there could be a better L forgery adversary. Okay, so to sum up, the idea in the first row is bad because we have epsilon equals 1 here. But what if we first hash the public key, then the message, and then the commitment? Note that with regards to the signature forgery attack, we can run the same attack as before. So here you can see again the Joule multi-collision. Again, the first hash state is known. Also in the case where we put the public key in the beginning, it's just the hash of a public key instead of the initialization factor. So that's why we get here the same factor. However, we can say that this here is preferable over the first variant as the factors here in the user exposure setting improves. And this improvement is achieved by the so-called Trojan attack. And the construction works like this. So we start from the hash of user 1's public key and find, starting from there, we search for a collision, M1 and M1 prime. Once we found it, we append M1 to hash of user 2's public key, and then we use the resulting state to find the next collision. Once we found this, M2 and M2 prime, we append M2 to the previous path. And like this, we proceed for all L users. So the next step would be taking M1, M2, and append this to hash of user 3's public key, and then again start to search for a collision. And at some point, the construction looks like this. And this is nice because now we have for every user 2 messages which map to the same hash value, and they also produce the same challenge. And why? And special about this is that all the flag messages are the same for all the users. And this makes it easy to run a user exposure attack, as the adversary can ask, again, the users to sign the flag message, which was the same for every user. And then she can use the user-specific red message together with the signature she has received in the first step. And here I was a bit too fast. To run that attack, the adversary only has to find L many collisions. So the runtime of this attack is L times the runtime to find a single collision, which is 2 to the n over 2 classical here and 2 to the n over 3 in the quantum setting. Okay, so the picture looks like this, but now it's again similar to the Joule multi-collision attack. We don't know if the Trojan attack is optimal. If it would be the case, it would be pretty nice, as then we can say, okay, it's actually annoying with a epsilon factor equals L, but we don't know it. But what we know is a lower bound for finding L collisions. And this lower bound is actually also a lower bound for running a user exposure attack. And in that way, we get our epsilon factors. It's L to the 1/2 in the classical setting and L to the 2/3 in the quantum setting. What is missing is the case where we hash the commitment before the message. How do these factors change them? At least what we can say is that the attack I showed you previously are no longer applicable. Recall that the commitment was the first value chosen by Alice, and all the others, challenge and response, depend on it. So in MLDSA, for example, Alice uses the public key, to derive a commitment, and she requires a secret key to compute a corresponding response. What does it mean for our adversary? It does mean it can do this step, but not the step later on to compute the response. So the adversary cannot just freely choose commitments, but actually must reuse them from honestly generated signatures. And this changes the nature of forging a signature compared to before, as the commitment only becomes known after the challenge is known. And consequently, the hash state for which we would search here for a collision is only known after the challenges. Thus, the adversary is no longer searching a collision problem, but a secondary image problem. And on one hand, our best known second pre-image attacks, which I don't want to explain further here because of the matter of time, in both cases, we get better annoyance factors. And on the other hand, these best known second pre-image attacks require exponentially long messages, which easily can be mitigated by suggesting a maximum length of the message. So that could look like if I have a signature scheme, I also specify a parameter saying whenever you see a signature to a message which has this length, you shouldn't accept the signature. And this is not a real restriction, as this parameter n for SHA-2 and SHA-3, it is at least 224. So this is a pretty big message, so it's not a restriction to say we just don't allow that. And this is why we concluded in our paper that when using Fiat-Shamir signatures, one should hash the commitment before the message. And with that, let me return to the zoo of Fiat-Shamir signatures I showed you in the beginning. We can see that all variants of Schnorr signatures follow our rule. The commitment is before the message, whereas MLDSA does something different. And what I want to say is not that MLDSA is insecure. What I want to emphasize is that the annoyance factors could have been improved if they would have done it differently. But yeah, I assume they won't change the standard there. Yeah, that's everything I wanted to share with you from my paper. Let me share with you some ideas for future work and open questions I have. So the one thing is this quantum-annoyance topic, what I personally find very interesting. So everything started here from the page. Then there is some other work which I would summarize as quantum-annoying public parameters. And we did the first step towards quantum-annoying signature schemes, but there are yeah, plenty of cryptographic schemes which one could analyze. And the other topic, what could be also interesting for like in other protocols than the Fiat-Shamir signature schemes is the question, in which hashing order should we actually input components into the random oracle model? So this phenomenon, having a protocol with different components and security proof in the random oracle model, it's nothing special to just have it for Fiat-Shamir signatures. There are other examples which one also could analyze. One obvious example is that the Fiat-Shamir paradigm is also used in the zero knowledge domain. So there also one could analyze in which order one should actually hash. And yeah, with this I would like to conclude my talk. If this talk sparked your interest, you can find my paper through this QR code or through this IRCR reference below it. And yeah, thank you for listening. And if you have any more questions, then I'm happy to take it.
Thank you. Any questions?
Just in high level is like to put the commitment first to kind of prevent the adversary to compute the hash states for relate to the message, right?
Yes.
And like my understanding is it used to be a convention, but like you formalize it and prove something, right? Or
yeah, I'm not sure if it's really a convention because
I think it's asking them why does all the standard recommend that one?
I mean it was only
Yeah. Well, why
Yeah.
all these standards recommend this order?
DSA does something different here,
Yeah.
right? So there the commitment is after the message.
yeah, but like for example, the other how to say, like for the first three,
Yes.
did those authors they propose something? Did they propose some similar ideas or some
No.
intuitions? Oh,
So I mean this is a very early paper. I'm not sure if Schnorr mentioned something towards the setting.
He happened to use this order, but he doesn't have a specific reason to do so.
Yeah. So I think he was like more focused on the single instance setting. The paper here of Bernstein was the first one who also considered multi-users, and he had some reasons to put the public key like at the beginning to prevent some attacks, but no one really formalized or write it down why you should do that. And I mean this is yeah, a very recent signature scheme, and it was standardized, I don't know, a couple of years ago. So it's a fairly new scheme, and they do it differently. So we hope with that paper to give some guideline for the next designers or next practitioner who wants to design signatures. Thank you for the question.
Any question? Can I go to that table for the epsilon?
Yes, Stefan.
Yeah. So here, like, I think we need to find the lower bound for epsilon instead of the upper bound, right? So,
Yes.
all these things here are upper bound.
Yes.
Meaning that you know very little about the lower
Yes.
bound.
So, yeah, you're right. It actually could be that the epsilons maybe are the same. So this is not a contradiction, but
How about in the middle cell? When you say epsilon equals L to the 1
Yes.
over 2, is this like strict?
this is strict.
But for example, on the cell below it, potentially epsilon could still equal 1.
That is correct.
Okay.
No.
Wait.
Wait.
It
No. So this is actually also a lower bound for here. So we know that No, I'm sorry. I need to look that up, but I think we also know some lower bounds.
I think my point is,
Yeah.
or maybe let me ask, who defined this notion for annoyance first?
For signature schemes,
Yeah.
this was us.
Oh, okay. So this paper.
Yes.
Yeah. I think this notion is not that well founded because I think a better way to put it is you need to consider the hardness. You really need to distinguish between the hardness of breaking the random Merkle and the hardness of the computational assumption. As I said, it's totally possible that just for Schnorr signature, I break DDH, use like t equals to the power square root of n, I break DDH.
Yeah.
Then like your epsilon is always one. Because as long as I break DDH, I can generate an arbitrarily many signatures, right?
Yeah, I think it's like related to, like, for example, in cryptanalysis, you also have this distinction where you, on one hand, try to attack the primitive, and on the other hand, you try to
Let me give you a constructive suggestion to modify this definition.
Yeah.
You first, I think at least for all your applications, let's use delta to define the time you found the collision for the oracle. Like just for example, if you're running Merkle-Damgård, it's just time you use to break one layer, for example, the innermost hashing. Let's denote that time as delta. Then you can say that in time big O delta, I can generate one signature. And in time something like epsilon times big O delta, then I can generate L copies of forgery. So my suggestion is you need to count the attacking cost in terms of the time you use to break the hash function. I'm proposing a new notion for annoyance. I think it should be defined in this way.
And you're looking like into the compression function.
No, I'm saying that let's say you have the ability to break Merkle-Damgård to find one collision in like time delta. Delta is just the state bound time.
Yes.
Then you can generate one signature in time delta. And then you can say that, okay, now I need L to the power 1/2 to generate L copies. In this way, you can exclude this discussion about the time you use to break DDH.
Yeah.
Right.
Yeah. I think we just like put a sentence there that we just assume that DDH didn't break and
infinitely hard.
Yeah.
I think the better way is to like count it in terms of the time you break.
But it's more than like the analysis you would change, right? Like the definition should be still okay to say that that L times runtime of A1 is a lower bound. Then you just would like refine the runtime of
technically you can use something like a minimum between the time you break DDH and the time like L times big O delta.
Yeah.
That will be accurate.
Yeah.
This is not accurate, to be honest. Yeah. You can because you can only say upper bound. You cannot put anything on the lower bound because of the possibility of break DDH. One reason is you break DDH.
Yeah. So the reason that we don't have a lower bound here is more that the second pre-image problem is not well analyzed, or at least we cannot find lower bounds.
But if you want to say that that's the only source or only reason you cannot find a lower bound, then you have to say something like, okay, then we assume DDH is infinitely hard.
Yeah.
Yeah.
But yeah, I'm not sure if I don't know, but use here the lower bound from the computational problem, then it could be still the case that it's easier to break the collision problem or to break the second.
I'm just saying that then you need a accurate mathematical notion to define that instead of leaving this as a or simply assume that DDH is infinitely hard. That's all my comments? Any more
Thank you.
questions? Okay. Yeah, that's thank the speaker again.